The kinetics of radioactive decay are very important. The time it takes for 1/2 of a sample to decay is called the half-life. Now, this is similar to drug pharmacokinetics, where the half-life of a drug is the amount of time it takes the human body to reduce the available drug to 1/2 of its initial dose. Now, the half-life of radioactive decay is independent of external influences, pressure, temperature, etc., since this is not a chemical reaction, but a nuclear reaction. Here we see some important isotopes and their half-lives. Notice that the therapeutically important isotopes like iodine and technetium have relatively short half-lives, 8 days and 6 hours. This is good because we do not want patients to suffer too much radiation damage from imaging procedures. We can compute how much substance is left from a dosage of radioactive material based upon the half-life. Here we want to determine the amount of iodine-131 left after 32 days. Using the given half-life as a conversion factor, we see that 4 half-lives have occurred in 32 days. This means if we take half of the initial dosage, then half of that dosage, then half of that resulting dosage, then half of that resulting dosage, we would get the final mass. In other words, if we multiply the dosage by 1/2 for each half-life, or simply the dose times 1/2 raised to the power of the number of half-lives, in this case 1/2 raised to the 4th, we see that after 32 days, 6.25 milligrams of an initial 100 milligram dose is left. Using the half-life of carbon-14, we can determine the relative age of archaeologic samples. If we compare the ratio of carbon-12 to carbon-14 in a living individual, we see that the ratio is constant. But once the organism dies, it is no longer taking in carbon-14, and so the ratio of carbon-12 to carbon-14 changes. Now, since the half-life of carbon-14 is over 5,000 years, we can use this to determine the age of some pretty old substances. Detecting radioactivity and quantifying it can be difficult. We use the unit the curie, which is 3.7 times 10 to the 10th disintegrations per second. And a disintegration are the number of nuclei that are decaying over a given unit time. The curie is fine for measuring a sample of radioactive material, but how much radiation is absorbed by living things is different. For that we have the rad and the rem. The rad is the radiation absorbed by 1 gram of substance. Now contrast that to the rem, which takes into account the energy of the radiation and its ability to damage tissue. So 1 rem of any type of radiation is the same. So 1 rem of alpha is the same as 1 rem of beta, which is the same as 1 rem of gamma, etc. Since radiation is all around, we are constantly exposed to it. On average, we take in about 0.27 rem of radiation per year. Biologically, damage starts around 25 rems, and 500 rems will kill 50% of the population that's exposed to it. This is known as the LD50, or the lethal dose that kills 50% of a population.